So in this video, we will initiate our discussions on gyroscopic motion of rigid bodies. Gyroscopic motions are, the analysis of gyroscopic motions are a little bit more involved than other simpler problems in dynamics, because gyroscopic motions are ones where we try to analyze motions of rigid bodies, or specifically rotations of rigid bodies, where these rotations are in 3 dimensions. And so sometimes the visualization or the intuitive understanding of this motion can become a little bit difficult. And hence we need to do a careful analysis and then try to understand each of the components well, to gain a better understanding of the nature of gyroscopic motion. So because of that, this topic that we are going to cover is going to take a few separate videos to cover, or perhaps several videos to cover, but we'll definitely not be able to finish it in 1 or 2 videos. It's probably going to be more. There are 2 main categories of gyroscopic motion that are studied in dynamics. One is in the context of gyroscopic motions of rigid bodies that are rotating in space. And the other is gyroscopic motion in the context of objects like spinning tops, where the motion is under the influence of gravity. The nature of gyroscopic motion for rigid bodies in space and is similar to the nature of the gyroscopic motion for a rigid body that is freely falling under gravity. So those 2 situations are similar in terms of the rotational motions. So in the first discussion, what we'll do is we will, so within gyroscopic motion, so we will first consider gyroscopic motion in the context of rotation of a rigid body in space. So this is the first category. Now here we will be considering a rigid body whose center of mass is not necessarily moving. We will, for the sake of simplicity, we'll assume that the center of mass is fixed at a certain point, but the rigid body itself has got rotations in all degrees of freedom. As we know, in space, a rigid body has 3 degrees of rotational freedom. And so we will consider all the 3 rotations, and then we will take a look at what is the nature of motion of the rigid body when all these 3 motions are combined. We will also consider free rotation, that is, the rotation of the rigid body when there are no external moments, or let's say also, for that fact, external forces. So free motion of a rigid body in space. And there are some very interesting observations that can be made upon analyzing the equations of the rigid body when it is undergoing just rotation in 3-dimensional rotation in space. So with that, we will first what we'll do is we'll try to define the orientation of a rigid body in space, an arbitrary orientation of a rigid body in space. And we are going to consider an inertial axis. Let's call it capital X, capital Y, capital Z. And this, the origin O, let's say that this is coincident with the center of mass of a rigid body. For the sake of simplicity, we can consider the rigid body to be a cube or a cuboid. So let's say that the rigid body is a cuboid. Okay. I've just readjusted the y-axis because we need to make this cuboid kind of initially aligned with the x, y, and z. So let's say that the x-axis is piercing through this face. This intersection should be at the center of the square of the or of the rectangle. And similarly, this axis, let's say, is piercing through the center of this face. So this is the initial orientation. Now, let us also say that there is a body fixed XYZ. The body fixed XYZ is a XYZ coordinate that is fixed to this cuboid and that rotates with the cuboid. So capital XYZ is inertial, meaning that it is, in this case, it is fixed in space, and small xyz is body fixed, and O is the center or the centroid, center of gravity. Because we are considering a symmetric, so the centroid will correspond to the center of gravity as well. Now, let us say that initially the rigid body is given a rotation about the z-axis, and let's say that rotation is by an angle psi. Okay, so if you consider this rigid body to be, let's say, an airplane with the positive x-axis in the direction of the nose of the plane looking outwards, and the tail being the negative x-axis, the y-axis being along the wings, then this motion and z-axis being directed vertically up through the center of this airplane, then this rotation is also termed as yaw. So in aerospace terminology, psi is going to be yaw. And when that happens, the small z, let's say it changes to z1. Now, because the rotation is happening about the z-axis, z and z1 are going to be coincident. The change that is going to happen is that small x will move to x1, and small y is going to move, or it's going to turn to y1. And these rotations are going to be psi each, right? So that's the first rotation. And so what happens when this rotation happens is that the whole rigid body turns, because x, y, z, or x1, y1, z1, these are all body fixed. So x1, y1, z1 is after yaw. Okay. Now next, let us say that we give a rotation by an angle theta about the new body fixed y-axis, which is y1. So we turn the rigid body by an angle theta about the y-axis or y1 axis. So this angle theta in aerospace terminology is called the pitch angle, and it causes, in the context of an airplane, the nose of the airplane to pitch downwards. Now with this, what's going to happen is you're giving a rotation about the y1 axis, that is the rotated body fixed y-axis. And let's say that as a result of that rotation, y1 goes to y2, and y1 and y2 are going to be coincident because you are rotating about the y1 axis. So y2 is going to remain in the same direction. But what's going to happen is x1 will now start pointing downwards, and that angle by which it moves downwards, and we'll call that x2, is theta. Okay. And similarly, simultaneously, z1 will move to z2, and it's also going to turn by an angle theta. Okay, so x2, y2, z2 is after pitch. Okay, and finally, let's say that, and so keep in mind that we are not showing how the rigid body itself is turning, because then the picture is going to become too busy here. But imagine that as these small xy are turning, the rigid body is turning with it, because by definition, small xyz are body fixed, right? The final motion that we give is a rotation about the x-axis, the new x-axis, x2. And that rotation is given by phi, and we call that roll. Okay, so that's an angle phi. So first the airplane goes like this, yaw, then it goes like this, that is pitch, and then it goes like that, that's the roll. Okay, so that's the yaw, pitch, and roll. Yaw, pitch, and roll. Okay, so the roll angle is phi, and it is about the x2 axis. So x3, which is the new x2 axis, will be coincident with x2 because the rotation is being given about the x2 axis. Now, as a result of this, the y2 axis will now climb out of the xy plane, and let's say it becomes this y3. Okay, and this angle then is going to be phi. Right, and similarly, when we make this turn, Z2 will also turn to Z3. So Z2 will turn to Z3, and that rotation is also going to be by angle phi. All right. So at the end of these three rotations, the rigid body would have taken a new rotated configuration. Now, these angles are also called Euler angles. And by the way, I should point out x3, y3, z3 is after roll. Okay, these three angles, yaw, pitch, and roll, psi, theta, and phi are called the Euler angles. And you need three Euler angles to completely define a new orientation of a rigid body. So a rigid body has 3 degrees of freedom of translation and 3 degrees of freedom of rotation. And so yaw, pitch, and roll provides those 3 degrees of freedom of rotation. Now the idea is that you can look at this. Now the question will be, why did we discuss this? The reason we discussed this is because our goal is to study the dynamics of the rotational motion of the rigid body, the arbitrary rotation of a rigid body in space. So hence, we need to define an arbitrarily oriented configuration of the rigid body, and we are using these Euler angles. The other way of looking at it is also that any arbitrarily oriented rigid body can be expressed as a orientation that is arrived at by a sequence of yaw, pitch, and roll in that order, psi, theta, and phi, to go from its initial configuration, which is given here, to the final rotated configuration. In other words, any final rotated configuration can be thought of as a configuration that is arrived at by providing 3 rotations, yaw, pitch, and roll, in that sequence following this convention of rotation. Right? And you can see that the sequence of rotation is Z, Y, X sequence. What we mean by this is that the first rotation is given about the body fixed Z, the second rotation is given about the body fixed Y, and the third rotation is given about the body fixed X. Okay, so the yaw, pitch, and roll essentially is a Z, Y, X sequence of rotations. Now, this is not the only way to define an arbitrary orientation of a rigid body in space. Yaw, pitch, and roll is popular because it is used in aeronautics and astronautics. However, you could also define the arbitrary orientation of a rigid body using other sequence of Euler angles. So Euler angles is not a unique set of rotations. As long as there are 3 independent rotations, these 3 will form a set of Euler angles. In some cases, for instance, you can have instead of a ZYX, you can have a ZYZ sequence of rotations, and that will also define a new or a unique orientation. So ZYZ would be where you rotate the rigid body about its body fixed axis by Z, then you rotate by the new body fixed Y axis, and then you rotate by the new body fixed Z axis. Okay, so that could be another way of expressing an arbitrary orientation of a rigid body as well. Now the mapping between if I take one point on this rigid body and I want to find the orientation or the coordinates of that point, I could use a rotation matrix. So in this case, I could use your rotation matrix followed by pitch and followed by roll and multiply them together. And that would give me the overall mapping between the original XYZ coordinate of that point and the XYZ coordinate of that point in the rotated frame. Okay. Or rather the XY coordinate after the rotations have taken place. So now that we have defined the angles that will be used to represent the orientation of the rigid body, these three angles will be treated as the generalized coordinates. So psi, theta, and phi would be the generalized coordinates in deriving equations of motion. Now, the most direct way of deriving the equations of motion is the Lagrange's equation. So I'm not going to go into the details of the Lagrange's equations other than just applying it here. It's a standard procedure for deriving equations. For the Lagrange's equation, for deriving the equations of motion using the Lagrange's equation, we need the Lagrangian, which is kinetic energy minus the potential energy of the object or the group of objects that are under consideration. In this case, V is equal to 0, since we are considering the motion of a rigid body in space. So it is just having rotations. Even within the in the kinetic energy, we don't need to consider the translational kinetic energy because we are considering only rotations of the rigid body. So in this case, the expression of the Lagrangian or the kinetic energy is going to become half Ixx omega, and I'm going to we'll recall that in this particular situation, the rigid body, when it is rotated, it now has x3, pointing in the direction where x was, or rather, let me put it this way: x3 is the new orientation of x, y3 is the new orientation of y, and z3 is the new orientation of z. And because these are body fixed and they are passing through the center of mass, and we'll also assume that this is a symmetric rigid body in the sense that it is the center of mass is at the geometric center. In that case, the expression of the kinetic energy is simply going to be Ixx omega x3 squared plus half Iyy omega y3 squared plus half Izz omega z3 squared. Now, the kinetic energy expression becomes quite simple because we are considering the body fixed xyz to pass through the center of gravity, and they're also the principal axis. So body fixed and xyz along principal axis. And because of this, we don't have the moments of inertia in the overall inertia tensor. So it's a diagonal tensor. And so when we multiply it with or when we do the dot product with the angular velocities, then we only have these terms. We don't have the product of inertia terms. So this is the kinetic energy, but we cannot work with this kinetic, or rather this is the Lagrangian, but we cannot work with this Lagrangian because omega x3, omega y3, and omega z3 are in terms of velocities. And to derive the equations of motion, we need these angular velocities to be expressed in terms of generalized coordinates, psi, theta, and phi. We need to express them in terms of angles, actual angles. And so this Euler angle comes into use here. And what we can do is we can, based on this orientation, we can try to derive the equivalent expressions for omega x3, omega y3, and omega z3 in terms of the rotations psi, theta, and phi. So let us say that the angular velocity due to psi is psi dot. Obviously, that is along the z-axis, inertial z-axis. The angular velocity, or the rate of roll, or rate of pitch rather, the angular velocity of pitch, we'll call that theta dot, and that will be along the y1, y2 axis. And lastly, the angular velocity of roll, or the rate of roll, will be phi dot, and that will be along the x2, x3 axis, or the x3 axis. So what we'll do is we will express omega x3, omega y3, and omega z3 in terms of theta dot, psi dot, phi dot, and theta, phi, and psi. Okay? And in the process, we will see that the new expressions are not only a function of theta dot, phi dot, and psi dot, but they also have in them theta, phi, and psi. So let's try to derive that. Now, first, we note that the omega x3, so we note that omega x3 is rotational speed in x3 direction. Okay. Omega y3 is the rotational speed in y3 direction. So these double quotes means that I'm just essentially copying the same thing down. And omega z3 is the rotational speed in z3 direction. So I want to express omega x3 using the angular velocities phi dot, theta dot, and psi dot. Okay. Now you can say that, well, omega x3 has to be then equal to phi dot, because phi dot and omega 3 x3 are in the same direction. But we have to keep in mind that omega x3, omega y3, and omega z3, these are mutually perpendicular. However, psi dot, theta dot, and phi dot are not. So essentially, psi dot, theta dot, phi dot are expressing angular velocities in three different directions, and they are not actually mutually perpendicular. In fact, you can see that while psi dot is in a fixed direction, it's the vertical direction, theta dot is actually a direction whose orientation itself is changing, because theta dot is in the y2 direction, and as the rigid body turns, the y2 axis also changes in direction. Okay, and phi dot is similarly in the x2, x3 direction or x3 direction, and the x3 direction is also changing in space. Furthermore, one very important observation that we can make is note that the direction of theta dot is going to be always perpendicular to psi dot. Why? Because theta dot, the direction of theta dot is always on the capital XY plane, the inertial XY plane. Why? Because y1, y2 are along the XY plane. So theta dot will always be perpendicular to psi dot. Okay. Similarly, theta dot is always going to be perpendicular to phi dot. And that is because theta dot is in the direction y2 and phi dot is the direction of x2, and x2 and y2 are mutually perpendicular directions. No matter what the rotations, no matter what the arbitrary orientation is of the rigid body at any instant, as we have seen, we can express the orientation using these three rotations. And once we do that, theta dot and phi dot are always going to be in the y2 and x2 directions respectively. And so they are going to be mutually perpendicular to each other. And you can see that intuitively as well. When you turn about theta, it causes x1 to turn to x2. So this was x1. It turned to x2. This is x2. Okay. And this is z1 to turn to z2, and this is x1. It turns to x2. But as it turns, it always maintains that 90 degree with the y2 axis. So phi dot will always remain perpendicular to the theta axis. So we note that theta dot is perpendicular to psi dot and theta dot is perpendicular to phi dot. These are very important observations, and they will be handy moving forward. But you will note that phi dot is not perpendicular to psi dot. Phi dot is not perpendicular to psi dot. Okay. In fact, you can see here that phi dot is making an angle of 90 plus theta with respect to psi dot. So we make a note that phi dot not perpendicular to psi dot. Okay. Now, with these observations, when we express omega x3, we have to note that omega x3 is the net angular velocity of this rigid body about the x3 direction. Okay. And so it is going to be, there is going to be the phi dot term. Theta dot is not going to have any component in the phi dot direction, because as we just pointed out, theta dot is always perpendicular to phi dot. But psi dot is not perpendicular to phi dot. So psi dot sine theta is going to be in the direction opposite to phi dot. So we have a minus psi dot sine theta. And that's the expression of the net angular velocity of this rigid body along the body fixed x-axis. All right. Now let us go to omega y3. The angular velocity, the net angular velocity in the y3 direction. That's the net angular velocity in this direction. Okay. Now this direction is lifted by an angle phi from the y2 direction. So then clearly theta 2 cosine phi must be there. Theta dot cosine phi must be there. So that is one component. Theta dot cosine phi will be an angular velocity in the y3 direction. Now, we know from our previous observation that theta dot is perpendicular to phi dot. Right. So, and by the way, yeah. So, sorry, that is not relevant here. When we go to find what is the component of phi dot along this y3 direction, we make a note that phi dot is in the x3 direction, which is perpendicular to the y3 direction, because x3, y3, z3 is a triad. So therefore, phi dot is not going to have any component in the y3 direction. But psi dot is going to have a component. Psi dot is going to have a component in the y3 direction. Because psi dot, if you resolve it in the in the z2 direction, is going to be psi dot cosine theta. Right? And then when we make the turn from y2 z2 to y3 z3, then we are turning the y3 and z3 axis. And so psi dot cosine theta will now get resolved along the sine phi direction to give me the y3. So let me just put the expression. So you'll have psi dot cosine theta sine phi with a negative sign. Let me check that. Cos phi. Oh no, it is a positive direction because this is forming. You see Z3 Y3 is forming a 90-degree angle, and Z2, which is this one, right, is within that 90 degrees. So Z2, so psi dot cosine theta cosine phi will be along the Z3 direction, and psi dot cosine theta sine phi plus sine phi is going to be in the Y3 direction. Right, and then we go to omega z3. Omega z3 is the net angular velocity in the z3 direction. So that is going to be the theta dot sine theta, but with a negative sign, sine phi rather, with a negative sign, because here you have z3 y3 forming a right angle, and theta dot is forming an angle of phi outside that right angle. So theta dot cosine phi resolves in the y3 direction, and theta dot sine phi resolves in the negative z3 direction. So it resolves in the negative z3 direction, and so we will have negative theta dot sine phi. Okay, and so that is one component. Now we also have z3 to be perpendicular to x3. So therefore phi dot does not have any component in the z3 direction, right? But psi dot does have a component. So psi dot cosine theta resolves psi dot on the z2 axis, and the z2 axis is between the z3 and y3, and it forms an angle of phi with the z3 axis. So essentially psi dot cosine theta cosine phi with a plus sign is going to be the resolution of psi dot along the z3 axis. So these three angles then forms the equivalent expressions for the body fixed angular velocities, and one can then express a mapping between omega x3, omega y3, omega z3 to the rate of change of the Euler angles, and they are psi dot, theta dot, phi dot, and we have minus sine theta, 0 and 1. We have cosine theta sine phi, cosine phi, and 0, and cosine theta cosine phi minus sine phi, 0, as our rotation matrix, net rotation matrix, that transforms or that maps between the body fixed angular velocities to the angular velocities along the Euler angles. So these will now, these expressions will now be substituted into our kinetic energy expression to get the Lagrangian from which we will derive the equations of motion. So we'll stop here. This is the first part of the video. As we mentioned, it's going to take a few videos to cover the whole set of results, or the whole analysis, and then go to the and then the results. So we'll be posting these videos as we explain this gyroscopic motion in detail. Thank you so much.